Yeah, I will start recording, introduce you, and then you can start.
Okay. Okay.
Recording in progress.
Okay, it's a great pleasure for us to have Haoyu as a speaker today. Haoyu got his PhD degree in physics from Harvard University 2 years ago under the supervision of Professor Tobias Sachdev, and then he started working as a postdoc at Cornell. Actually, even when Haoyu was an undergraduate student, he did some very impressive work on Fermi liquids. Then during his PhD study, and now he has been doing some very interesting work on non-Fermi liquids. In general, Haoyu has been working on strongly interacting systems, and I would say one of Haoyu's distinguished styles is he's technically very adorable. When I attended his talk last year at KITP, I was fully impressed by how technically strong he is. Today, he is telling us about his new work on circuit dynamics. Yeah, Haoyu, please go ahead.
Okay. Thank you, Liu Jun, for the invitation and the very nice introduction. Okay. So today I want to tell you about my venture into still fermionic system, but more with a more non-equilibrium flavor. So the title of the talk is a few theory of monitored interacting fermions with charge conservation. So this work was in collaboration with Professor Matt Foster at Rice University, Professor Chao Mingjian at Cornell, and Professor Andreas Ludwig at the UCSB. And here is the archive reference. Yeah, so just let me start by some general motivations of why I think this is an interesting problem. So, for example, I want to start with quantum entanglement, which is a distinctive feature that separates quantum mechanics from classical mechanics. So, quantum entanglement basically means that in a quantum state there contains some non-local correlation inside the state. For example, in this EPR state, if I just measure one spin A, I could know the value of the other spin B, which is in the opposite direction. And I could do that even if those two spins are very far apart. So this is what Einstein called why Einstein didn't like quantum mechanics. He said this is a Sputski action at a distance. But later on, we knew this is just how quantum mechanics work. So quantum state could encode non-local correlations. So nowadays, people more or less view quantum entanglement as a resource for quantum information processing. If you want to do some, you use entanglement as a resource. You consume EPR pairs to do some information manipulation. And also from the more many-body perspective, now people also understand the entanglement as a mechanism for scrambling and summarization. Right. So one great usage of quantum entanglement in many-body physics is that we could use it to classify all the different states. So, for example, one way of doing this classification is to look at the entanglement entropy of a system. For example, we divide the system into two subregions A, and it's a complement bar A, and then we calculate the entanglement between these two regions. Then, depending on, for example, how those entanglement entropy scales with the geometry of this region A, we can classify them into different states. For example, if we have a ground state of a gap quantum system, the entanglement scaling is area law. But if we have a generic excited state of a manifold system, which is a finite energy density, the entanglement scaling is going to be volume law. Then in some more exotic cases, for example, some CFT coming from quantum criticality, we get a logarithmic scaling with a log violation. Yeah, so today's talk is really about trying to understand the dynamics of entanglement. So a playground for studying this sort of problems is those quantum circuits or those monitored quantum systems. So basically, there are two important ingredients of this dynamics. One is the unitary evolutions, which are illustrated by these two-sided unitary gates. And then from time to time, we also try to measure the system. This is shown by those blue circles here. And today's talk is about trying to understand the dynamics of entanglement when the system has both unitary evolution and has measurements. So in general, from general grounds, we actually expect these two things to do very different things. They have different trends to the entanglement. So, for example, if we think about unitary evolution, it usually generates entanglements inside the system. But once the system starts interacting, it will try to entangle different parts of the system. And then once you let it evolve for a long time, you will generate a long-range entanglement. So one example of this is how a system locally becomes thermalized. Say, for example, you start from a pure state, and then it is the pure state you start with is very non-thermal equilibrium like. So if you look at how a local observable the probability distribution of that is very non-thermal. But now if you just let the system sit there and then let it evolve for a while, and then you go back and look at those local observables, you will see its distributions look very much like a thermal equilibrium distribution. The state still stays pure globally, but because of the generation of entanglement locally, the state it looks like it's been thermalized. And then another ingredient is measurement, and then measurement actually do very different things. It tends to reduce the entanglement of the system. So the extreme limit is the so-called quantum Zeno effect. Is that if I just keep measuring the system, I could almost with probability 1, I could quench the system inside its initial state. So this is illustrated by this cartoon here. So suppose I start with a wave packet and I let it sit there and then do not measure it, it will just spread away. Then if I measure it from time to time, you will see that once I measure it, the wave packet will collapse, and then it will be localized somewhere. But suppose now if my measurement rate is very high, I just keep measuring the system with very high frequency, then the wave packet has no time to spread out. Then every time I measure, the wave packet will just collapse back into the region where it started. So that means that if we keep measuring the system will be quenched in this initial state. And this initial state, if you look at its entanglement with the rest of the system, it has a short range entanglement, which has a error loss scaling. So now we see that when we have both unitary and measurement, the entanglement of systems seems to they want to do different things under these two different dynamics. So if we so this brings up the concept of a measurement-induced phase transition. So suppose we could just continuously tune the strength or the frequency that we monitor the system, and then when we monitor the system a lot, we expect to get area law, but when we do not monitor it, we expect to get a volume law. Then people have a conjecture that in between there could be a phase transition where the scaling of the entanglement will changes. And indeed, people have seen those kind of transitions in numerical simulations in some qubit systems. So and many people have worked on this topic. So this is an example of 1+1D numerics where in depending on your measurement rate, you either get an area loss state or a volume loss state. But in between at the transition point, the scaling is a logarithmic scaling. Yeah. So since MIPT has been proposed, it has been I think it has been mostly studied in the platform of random quantum circuits. So now those unitary gates that act on this two neighboring qubits, drawn randomly from a hard measure. So people choose to do it this way because it's the averaging procedure could bring up some simplification in both in both theoretical computations and also numerical simulations. Right, but in this work we try to study this problem from different angles. So we want to think about a system that is more familiar to condensed matter physics, which is just a fermionic system. So here the unitary dynamics of system is very simple. We just have a spinous fermion that's moving on lattice, and they could have density interactions. So then on top of that, we will try to put the measurements into the system by monitoring the densities of those fermions. So so we could do it either with a strong projective measurement and then control the measurement frequency, or we could do it with weaker measurements and then tune the strength of the measurements. So in either way, the continuum long scale field theory description of those systems will be the same, and then these microscopic details will not matter. Right. And since we are working with fermions and we're working with complex fermions, so those complex fermions are special in the sense that they have a conserved charge. So with the conserved charge, there is actually more. There's a little bit more physics than just thinking about the entanglement of system. So since we are the problem is kind of phrased in the following way, is that since we are just measuring the charge of a system. So basically, I'll collect a bunch of measurement results saying that at the location R1 at time T1 there is or is not a charge. So I'll get a bunch of those measurement results. So the question is asking, like, suppose I have a super powerful computer or some sort of thing. Is it possible for me from those measurement results? Is it in principle possible to reconstruct exactly how many charges was there originally in the system? So you can think of this problem also in the two limits. So for example, if I just measure the system so strongly in the quantum zero limit, then all the charges will just be localized in the system. They will be quenched. Then I will just I can just add our measurement results, and I can get a number of how many charges are there in the system. But on the contrary, if I measure the system very rarely, then all I get is that I know there is a charge somewhere, but then after I measure, but after I measure it the next time, you might have moved away from that place. So also all I could get is an average charge density, but I wouldn't be able to know how exactly is there exactly how many charges are there. So right, so there's so conceptually you can see there's a transition between whether you know or you do not know how many charges are there inside the system. So this is also called the charge sharpening transition. So the phase you know how many charges are there is called the charge sharpened phase, and the phase you do not know is called the charge fuzzy phase. And before people have tried to study this system in the context of random quantum circuits, and what they found is that this transition seems to only happen inside the volume law phase, but then it does not happen in the area law phase. So one of the questions we will try to answer is from a symmetry point of view why this is the case. Right. So, okay, before I actually get to the problem, let me just also briefly talk about why, since I have more of a hard condensed matter background, why do I think that problem is a fun problem to work with? So usually when we, as a condensed matter people, when we want to think about a non-equilibrium system, it's usually very hard to analyze. For example, all the most thing we do is to try to write down a Boltzmann equation to describe a non-equilibrium system, and then to actually know about the system, we have to actually keep track of all the occupations of all the energy levels inside the system using a distribution function. But if we look at those monitored systems that we are studying here, it's actually a very simple type of a simple class of non-equilibrium quantum system that we could describe as phases and phase transitions. So the main physics that comes into here is that since we are keep measuring the system, we actually the measurements actually will actually heat up the system to such that it looks like a infinite temperature state. Because the average density matrix looks like it's the identity matrix. So this means that there's no distribution function for this system. It is just a trivial function. It's a constant, not zero. And then following from that, we could actually show that those measurement-induced heating actually can lead to an enhanced symmetry of the system. So suppose your system in equilibrium has a symmetry only G, then in those measurement setup you will have a symmetry G cross G. It's getting doubled. I will try to talk more about this in detail. And therefore for this non-equilibrium system, and then if you think about it, because it has enhanced symmetry, so its effective field theory is actually quite constrained. So we could actually actually write down a relatively simple effective field theory. And then it's another nice property of this effective field series is that it could be mapped to a classical stat-mech problem, which I will also try to describe later. Yeah. So okay, before I get into details, let me just show the phase diagrams that we are trying to propose here. So the phase diagram is there are two axes. One is the measurement rate that we monitor those fermions, and the other axis is how strong are those fermions are interacting. And we see that there are only three phases. So the entanglement has two entanglement phases, which is the volume law and the area law phases. And then the inside the volume law phase, it's getting enriched by this charge sharpening transition. So there's a charge velocity phase and a charge sharpening phase. So we'll see that this problem can be mapped to the stat-mech problems, and then one of the results is that if you just think about free fermions and you monitor it, that there is only an area law phase, and then there is no volume law phase, so you wouldn't see a transition. So that's why we need to consider interaction here. And then we also understand why the volume law phase gets separated into those two charge phases. Based on symmetry, and why this separation does not happen inside the area law. Right, and then the symmetry group G of the system, it's just spanned by the charge U1s and the permutation symmetry when we try to replicate the system. And we also understand the phase transitions between all those phases. For example, the entanglement transition is a symmetry breaking transition that could be described by Ginzburg-Landau theory, and then the charge sharpening transition can be thought of as a costless Taoist transition. And then there is something we think that could be there's some different scenarios when we think about how did these two what's the relationship between these two transitions. That's here what we call scenario 1 and scenario 2, which I will try to talk about later. Any questions so far? Okay. Right. So let me just talk about how this problem is set up. So right. So so basically what we're doing is that we start with a quantum state of the fermion system. We let it unitary evolve for a while, and then we measure it. And then once we measure the system, of course, there can be multiple results. And then for a particular shot of your experiments, you will get one result, and then the system collapses, and then you keep doing that, it evolves, and then measure it collapse, and then it goes on. So this set of measurement results is what we call the quantum trajectory of the system. So it's a bunch of density measurement results, which we call V1, V2, and V3. So basically, based on that, you could you could write down how does so once I tell you a set of quantum trajectories, you could write down how does what's the density matrix of the system after the kind of unitary plus measurement dynamics. So what you do is that it evolves by the unitary, and then once you measure it, you apply a so-called Krauss operator onto the density matrix, which is you can think of it as a generalization of the projection operator, and then you let the unitary evolve for another while, and then you measure again, you put another Krauss on it. And then so this density matrix D of V here is not normalized, but its trace has a very physical interpretation. Is that the trace of this unrenormalized density matrix D is just the Born probability of getting the particular set of measurement outcomes, which is the probability of the quantum trajectory V. Right, and then another theoretical background that we will need to use is the so-called replica trick. So this is because the MIPT is defined by thinking about the entanglement entropy of the system. So we need to find a way to calculate the entanglement entropy of a subregion A. So to do that, we need to think about a nonlinear power of the density matrix, which means that we need to replicate the system. So so generally, let's think about the nth order Renyi entropy of the system. So its definition is like that, and this is average over all the quantum trajectories. So to and then the way to compute this kind of a trace A of rho A to the nth power is to try to think about multiple copies of the system. So so here using some linear algebra tricks, we could write this trace of the reduced density matrix rho A to nth power. We can write it as a trace of the density matrix of the whole system to nth power, and then contracted with a replica permutation operator. So what this operator does is that it looks at where you are inside the system. If you're inside the subregion A, you will try to permute the replica of the system. If you are outside of subregion A, it does nothing. So this is a way to generate this kind of a trace all the way to the nth power. And then after that, the thing you need to calculate is something like a trace of rho n to the nth power contracted with Cn. And then the next thing you need to do is to try to compute this log here. So with this to compute this log, we will do a second replica trick. So basically, we are using that formula, which rewrites a log of x as x to the nth power -1, and then to take that limit. So basically, we will try to decouple the log with another number m, and then it ends up that we need to evaluate this thing, which is this density matrix of d of v that's replicated 1 plus n m times. So the total number of the replicas we need is n times n plus 1, and then when we take the replica limit, this r goes to 1. So why is this limit 1? Is because here we are weighing the different quantum trajectories with their Born probability. So this Born weight will contribute another copy of the system. So this is very different from say if you are familiar with the disorder electron problem, which where the replica limit is 0. And the final thing we need to do is we try to think about what those two equations are saying. So we could actually try to interpret those entropy as the difference of two different partition functions. So the first one is a trivial partition function where we just copy the system n times n plus 1 times. And then the second function is sort of different, because here it is multiplied with this replica permutation operator. So we can think of it as a boundary condition that we impose on this system. So once we try to interpret those partition functions as some sort of free energy, then the entanglement entropy is actually just is trying to calculate the free energy difference between two different boundary conditions that's imposed at the final time slice of our evolution. So now, for following that picture, it will be somewhat transparent that this thing have a very nice analogy with a condensed matter stat-mech problem. So first, let me just talk about how we think about a ferromagnet. So suppose I have an Ising ferromagnet which has a Z2 symmetry. So how do I say that this system has symmetry breaking and has a ferromagnetic phase? So now the way we do it is we try to apply a perturbation to the system at a boundary. So say we up at the boundary we just put a magnetic field there, and then inside region A the magnetic field could change sign, but then outside of the region A then the magnetic field always has a fixed sign. Say it's negative. Then what we do is that we try to flip the sign of the magnetic field that we apply at this A slice of the boundary, and then we try to ask how different is the free energy, and then those difference of free energy has quite a different behavior depending on whether the Z2 symmetry is broken. For example, if the Z2 symmetry is broken, then the system will tend to order. Then it will order according to the perturbations that you put at the boundary. So basically what happens is that because the region A and A bar, the magnetic field now can have a different sign. So the bulk attached to this region A will have one sign of magnetization, and the bulk attached to region A bar will have a different sign. So and then you see that then inside the bulk there must be a domain wall between these two different magnetizations. And then this domain wall will make the dominant contribution to the free energy. That's basically saying that, and then the length of the domain wall, you can think of it as this is proportional to the length of region A. So it means that the free energy difference now is has a volume law scaling. It's proportional to the length of A. But on the other side, if you are in the Z2 symmetric phase where the system is disordered, then this difference of different boundary conditions, they do not influence the bulk. So all the difference you could get is at here and here. So the free energy difference you get is area law. So it's only sitting at the boundaries of this slice A. Right. So now, if we go to the measurement-induced phase transitions, it's actually very similar. So the symmetry we are breaking is the SR cross it's the copy it's the double the permutation symmetry between the replicas. So what we're also the full symmetry of the group is SR cross SR. But then when it's spontaneously broken, it will be broken down to its diagonal subgroup. And then following the same argument is that if once the symmetry is broken, you will get a domain wall in the bulk, and then because of the domain wall tension, you will get a free energy difference, which is the same as the entanglement entropy. So that's why you'll get a one law scaling. And then if the symmetry is not broken, you are in the other side, you get the area law scaling. So this is the yes.
How should I understand why the symmetry should be broken to the diagonal subgroup?
Right, because the diagonal subgroup is kind of the natural thing you would expect because the diagonal subgroup just means that when you act on a density matrix, you act by conjugation. This is the natural thing that you would do on a density matrix, and this is so-called a weak symmetry should always be there. And then this SR cross SR are double the symmetries that you could act on the left and the right of the dense symmetry using different matrices, and this is the unusual thing, which is what people call the strong symmetry.
But in principle, I can imagine the situation where it's broken to some other subgroups. Do those cases have any physical meaning?
No, I haven't thought about that, and right, because okay, in some ways it's that the diagonal subgroup, it's always there. It should be a symmetry of your whole ensemble, so it should always there, because
Yeah, that's the smallest symmetry, but I can have some bigger symmetries.
yeah, that could be possible, but yeah, we don't know of any example here. Yeah, maybe I don't know how to set this up. Yeah, maybe it's like saying that the group G cross G, you break to some subgroup like H cross H. Yeah, maybe with some, maybe if you engineer the dynamics carefully enough, maybe that could happen.
Thanks.
Yeah, so right, so this is basically the picture of how the symmetry breaking picture understanding of MIPT. So the question right now is how do we what's the field theory or the Ginsburg-Langdal theory for that kind of phase transition? Right. So now we need to actually derive a field theory for this problem we are thinking about. So the tool we are going to use it is the so-called the Keldysh field theory of non-equilibrium quantum systems. So a very nice introduction of this topic is the textbook written by Kamenev. So the idea of the Keldysh field theory is kind of is following. So let's just talk about the unitary evolution first. So when we try to evolve a density matrix, you will act a U and U dagger on the left and the right hand side of the density matrix. Then the usual sort of path integral is trying to turn this U of t into some kind of integration over all your histories. So the Keldysh idea is that it's now okay. I have a U on the left and a U dagger on the right. So let me just do that with two copies of path integrals. So effectively, that means that my time contour now is doubled. So this the first half of time contour is accounting for this U of t evolution, and then the second half is accounting for this UT of dagger evolution. So right, so the path integral get is just contains two actions. So it has two copies of fields, psi plus and psi minus, which has corresponds to these two copies. And then they had the relative sign. It says there's a relative minus sign because the difference of U and U dagger. Okay, now this is about the unitary part, and then how do we think about the measurement part? So right, so what we are doing here is that we in the continuum limit we try to implement those measurements using the so-called the weak measurement implementation. So now we choose those cross operator k of v. So this k of v, we choose it to be the following form. So this v could take value 0 or 1, and then this n is the density operator, which also takes value 0 and 1. So you see that so with this choice of cross operator, you can see that when kappa is infinite, you will become the projection operator that projects onto n equals to v. But then now we allow kappa to be finite, and then we could take the continuum limit of those operators. And so the evolution of this matrix, as I've shown earlier, it's just concatenating those U's and the K's. And now what you need to do is to trauterize those path integrals and then turn this of K into a coherent state path integral of the fermions. So at the end of the day, the result is that you get some additional terms in entry to the action that accounts for the measurements. So you see the one different thing is that unlike the unitary term, which has the opposite sign between the two contours, the measurement part, it has the same sign. And this measurement action is pretty simple. It's just it looks like it's just coupling those density of the fermion side by side to the corner structure V of RT. And you can see that this look very much like a coupling fermion to disorder, except that this disorder now lives in both space and time. And then we also need a Gaussian way for this disorder V. So in the continuum limit, we choose to be Gaussian. But in the original language, it is just literally saying that we are summing V between 0 and 1. So we are now just try to discretize those binomial distributions. When we cross grain it, it could become a Gaussian. And by the way, there is a
question. Yeah. Suppose I didn't do the detailed calculation and I just want to guess this form of the action. Can I do that?
Yeah, I would say it's maybe easier to guess the effective field theory than guessing the fermionic action, because there are various subtleties on trying to derive that coherent state path integral. So maybe I would. So here is so the next slide is kind of related to that. Is that in the quantum info community, people have another language which is they try to vectorize the density matrix and then do it with those Choi-Jamiolkowski isomorphism, and then you see, depending on the formalism you choose, there are different plus and minus signs and so on. So yeah, I wouldn't say it's easy to guess. Well, you can guess it up to those relative plus, minus, and i's. So that depends on your standard, I guess.
Okay.
Right. So yeah. So here is another way that the other people in the quantum info community tend to do that, is that they will try to map the density matrix into a vector in the double Hilbert space. So basically by acting row cross identity on the EPR state with the auxiliary Hilbert space. So for example, you could choose the phi such that the psi A dagger has a minus sign, but psi psi has the same sign. And then basically what you get is that the time evolution now could be to look like a Schrodinger equation, but the measurement part of a Hamiltonian is not Hermitian. So we have showed in our paper that if you implement this map carefully, and then you think about how you turn this Schrodinger equation into a path integral, the result is actually the same as what we do in Keldysh. Right. So now we will try to analyze this fermionic path integral. So since it very much looks like a fermion coupled disorder, so we will just follow the strategy of disorder fermions. The first step is just to look at the saddle point of the action. So right. So at the saddle point, just basically calculate the correlation functions between the fermions. So there are three correlation functions, which is the retarded and the Keldysh Green's function. So the retarded Green's function of the fermion, it looks the same as a disorder problem. So basically, because of the measurements, the fermion they get a lifetime which looks like it's coupled to disorder, and this lifetime is determined by the measurement rate of the fermions. And what is interesting here is that then you think about what's the distribution functions of the fermions. So this is related by encoded in the Keldysh Green's function via the distribution function f. So if we were doing a problem with thermal equilibrium, this f of omega, it will become a tangent function. However, for our measurement problem, this is very different because of the measurement process actually infinitely heats up our system to infinite temperature. So what we get is this f of omega is just a constant, a number that's related to the average density. So if the system is a half filling, so you can probably guess the number is 0. So right, so this problem compared to the equilibrium disorder problem is actually much simpler because we do not have a distribution function f to worry about here. Right. So
question.
Yes.
Question. So where is the interaction effect going? Actually, I think that's the content of the next slide. So you had some interaction between fermions. That should be encoded in SH.
Yeah, interaction is inside SH as a hopper U. Yeah, in the continuum. Yeah, it's just side by side squared. But at the
And
setup
in
point
the
level, it's hidden in those parameters. For example, this gamma could be renormalized by interaction a little bit. But yeah, I'll try to talk about I want to talk about the free theory first, and then from that after that I want to put the interaction into the system.
Sure.
Right. Another consequence of this infinite temperature thing is that say suppose you think about free fermions, then the system has an enhanced symmetry. It has a UR cross UR it has a UR cross UR rotation symmetry that acts on different replicas. So in the action, this is sort of obvious. Suppose the action is quadratic. So yeah, you explicitly see that there are two independent rotations. But in equilibrium system, this symmetry is secretly broken because because when you do equilibrium system, there is this Coulomb-Martin-Schwinger boundary condition they need to impose on the fields that the kind of that secretly break that symmetry. But in our measurement problem, this is actually a true symmetry of the action. So so suppose it's a pre-fermion, this UR cross UR is really there. And then suppose you have interactions, this UR will be broken down to the permutation symmetry between the replicas. Right. So okay. So after a setup point, we just think about the fluctuation about the setup point, and then that's how we derive the low energy effective field theory of the system. So right. So the effective field theory is a nonlinear Sigma model. So it has two sectors. So right, so still I want to talk about the non-interacting limit first. So right, so the first sector is the total charge of the fermions. So since the charge are just being kicked around by the measurements, so we expect the charges to just diffuse. So indeed we do get a diffusion theory. So basically, our diffusion theory has two bosonic fields theta and phi. And then there a particular linear combination then could be related to the average density of fermions. And then if you calculate the error correlation, it's indeed it has the form as a diffusor. And what's interesting here is that there are just no way for those fields to couple to the external electric field. You can think about it because the system is effectively at infinite temperatures, and then the infinite temperature system it cannot talk to electric field. Right, and then the second sector is the entanglement sector of the fermions, which is a SUR, a principal chiral nonlinear Sigma model. So the action is pretty simple. It's just a kinetic friend of a matrix field X, and the non-trivial thing is that the X field is it's a SUR SUR matrix. You can sort of think about as the fermion bilinears across the two contours of the Keldysh formalism. So again, if you look at that action, you can see that the system actually has enhanced symmetry because you could rotate the matrix X on the left and on the right independently. And another interesting thing is that although we started from a theory in real time, but the effective field theory that we have derived it actually has a Euclidean signature. So this is what it means that the system is effectively a StatMech problem. So we actually got an effective field theory in the Euclidean space. Right. So now, if you just think about what's the fate of this free fermion problem under measurement, you can realize that it actually does not have a phase transition. So this is because once you calculate the Archie flow of the the field theory, you find that the stiffness lambda it wants to flow to zero. So in 1 plus 1d. So that means that stiffness is zero means that the field they will don't want to fluctuate. That means we are actually in the disorder phase, which is the area law phase, and then there's no way we will get a volume law phase. So this is what people have been working on before. So before us, people did a free fermion field theory, and they didn't find a transition. Okay, now, so that's why we need to put interaction into our problem. So we need that for the volume law phase. So then to put interaction, there are two ways we could do it. So we first did it the hard way, which is to just do it with Fermion diagrams. So basically means that when you need to expand the trace log action and then expand it to higher order interaction. So what we need to do is to expand it to fourth order. So and then those are the important Fermion diagrams that we got. So it's for those people who do interactive fermions, we will recognize these are basically the self energy and the vortex fractions. But later we realized that there is a much simpler and more elegant way of deriving the same result, which is because we're thinking about complex fermions with density interactions. So we could to get interaction, we could basically just to gauge the U1s of those fermions. So basically, the U1s we get basically there are two copies of U1s on the two contours. So we can think of gauging them by these two auxiliary fields, phi plus and phi minus, and then and then after that you just integrate out those fields with a Gaussian action. Right. So now what we get is that we get two new terms because of interactions. So the first term is a density interaction. So the current interactions that's between the nozzle current of the nonlinear sigma model, and then the second term is an isotropic mass term. So it's a most oriented write down is so it's a xab to the power of 4 for each matrix element, and you sum them together. And then once you expand this x to the fourth term near the identity matrix, you realize that it is actually a mass term for the quadratic fluctuations. So you will get out the non-diagonal modes of the Lie algebra, and then what you are left are the diagonal fluctuations. So it means that on the mean field level, this term will want to favor the ground state where xab square is it's proportional to the identity matrix delta AB. And right, and then for this action, I think it's probably much easier that you could guess it based on symmetry. So the symmetry you use is a G cross G, where G is the semi-direct product between the U1s and of each replica, and then the permutation between the replicas. So and these two terms are the lowest order terms you could write down in the effective field theory.
Question?
Right. Yes.
So here this gauging trick, is it just to introduce some auxiliary fields and such that after integrating them out, I reproduce the original action?
Right. So you can exactly reproduce what we got from Feynman diagrams. Yeah.
Uh-huh.
Well, physically,
but
you
this
could think about it. Okay, so there is some density interaction is mediated by some scalar fields, and then the scalar fields they
okay.
get an action yield because, for example, it's screened by the fermion, so it has a charging term. So it's
Yeah, but this is exact. This is exact. The previous calculation is perturbative.
right. Yeah. This is
Also,
perturbative. Yeah.
Also, here you emphasize we are dealing with density interaction. In principle, we can consider other U1 symmetric local interactions. Then some part of the derivation will be modified. But is
Right.
the effective field theory modified?
As long as
Maybe
you
not.
come from as long as it has a U1 structure, I guess it will probably be similar. For example, here, if we do density, so you see the nozzle current here, we just get the time component. But yeah, if you imagine if you do it differently, there is a spatial component as well.
Okay.
Right. So so the next thing we did is that now we get an interacting theory. Now we try to understand what this theory is doing when we when we do RG. So this is what we down. So basically for RG, what we got is that the new term is this density interaction gamma, and this is a mass term n. So we found that this gamma it's actually fighting with the measurement. So for example, this gamma you try to slow down the flow of the stiffness toward the area law phase. And then for the mass term, we see that this gamma term actually, even if you do not start with a mass, this gamma will generate a mass term along the RG flow. And then it's no surprise that because the measurement is fighting with interaction, the measurement wants to reduce the scaling dimension of the mass term, so it tends to suppress it. And then also this definition gamma bar has a particular scaling dimension. And then what's difficult in this calculation is to getting this number 5/6, which took us like a few hundred diagrams. So yeah, but at the end it's just a simple number. Yeah. So
So just to confirm one thing, according to your answer to my previous question, do you mean this action is not the most generic action with that symmetry?
it is the most generic one.
What
but
about
depending
the
on how you expand,
spatial?
there are many high order terms you could imagine you could write down. But to the lowest two orders,
So,
I would think these are the two terms.
so here the current only involves the time component.
Oh yeah,
The
yeah. Of course, you could try to generalize that with the spatial components as well. Actually, when we did RG, we assume it has a relativistic symmetry. So both the time and the space are both there.
Sorry, you said you assume in the RG you assume both terms are
Yeah.
present.
So in the RG, this is actually J mu J mu. It's not not just
I see.
JT squared. Yeah.
Uh-huh.
Yeah. So yeah, yeah, so modulo whether you want to put another microscopic current a ampere interaction there, so it is but from the power counting sense, it is the kind of the generic from the replica structure, it is the most generic term. Yeah.
I'm asking because if I just include one of these two, then in the beta functions I may be missing some terms. Because on the RG, other metric terms will be generated.
Yeah,
But because you do include both, maybe it's fine.
yeah, right. You could imagine if you do not have the relativistic symmetry, then of course also of things could be there, but right. But yeah, but we when we're doing that part, we just try to simplify problem to assume our problem
Yeah.
have
But
relativity
mhm.
symmetry.
Yeah, but assuming relativistic symmetry here means the velocity that is involved in the first term, in the gamma term, is the same velocity as in the m term. M doesn't have any velocity. Oh, m is just a scalar on the
Yeah, m is just
range.
scalars.
Okay. Yeah, now I understand. Okay, thanks.
Yeah, so this is what the flow look like. So we could see there. So in the particular regime, you can see seems to be two trends. So in one direction, the mass wants to flow large, and then this is corresponds to Walton law, and then in the other directions, the stiffness wants to flow to 0 first. So this corresponds to area law. Right. So yeah. So this is what we have for the entanglement transition. So in the last few minutes, let me talk about what's happening inside the Walton law phase. How do we think about the charge physics? So suppose we are already inside the Walton law. So that means that the non-diagonal modes of the matrix X has been gapped out by the mass term. So now the remaining fluctuations are basically the phases that's living on a diagonal. So you can write them as a e to the iy. So which carries the U1 symmetry of the individual replicas. So you see, because the way we write it, since this e to the iy is naturally compact, so this compact field you could have vortices. So then you could think about whether the so once this vortices proliferated through a BKT transition, it actually exactly it actually exactly it described the charge-sharpening transition that I've introduced earlier. So yeah, so the symmetry breaking pattern of the charge-sharpening transition is that yeah, you first think about you have r copies of u1, two r copies of u1. So you first factor out the u1, which corresponds to the total charge of all the replicas. This does not break. But then you think about the relative u1s between the different different replicas. So the charge-sharpening transition exactly means that we break this the relative u1s down to its diagonal subgroup. So the broken face is fuzzy, and the unbroken face is called the sharpened. So and then we can actually write down the order parameters from our field series. So the u1 order parameter is just it's x itself, and the order parameter for the permutation symmetry is it's x squared. So from these order parameters, it's also very natural. You understand why only the Wallen law phase could have this charge sharpening transition. It's because if you want to break the U1s, you necessarily you have to break the permutation first. So because of this relationship between the two order parameters. Right. So, okay, the final thing that I want to talk a little bit about is the relationship between these two phase transitions. So, right. So the question I want to ask is that these two phase transitions they stay always as two separate second order transitions, or could they merge into a single transition? So the answer seems to be that both cases seems to be possible. So this thing is sort of similar. So this kind of a problem has been studied in condensed-matter literature called the intertwined it's called the intertwined intertwined Worcester order. So the original version was that was in superconductivity is that apart the superconductivity order parameter, apart from the U1 symmetry, it could also carry some Z2 nematic symmetry, for example. Then people ask the same questions, whether what's the relationship between the two symmetry breaking transitions. And it seems from the past work by Raphael Oz and York, it seems that two cases are both possible. They could either stay separated, or they could merge into a single first order transition. So right, so yeah, and right, so I guess that's all I want to talk about. And then so this is my summary slide. So this is our field theory, and then the effect of interaction is to break this SUR non-linear model, the symmetry, down to a permutation symmetry, which we have deformed the SUR manifold with these two additional anisotropic terms. And then we have a symmetry understanding of the entanglement transition as a spontaneous symmetry breaking of the permutation group, and then the charge-sharpening transition as a BKT transition of the U1s. And then I could take more questions.
Okay, thank you, Haoyu, for the very interesting talk. Any other questions? I have a question. Suppose I change U1 to some non-abelian continuous symmetry, like SU2. In principle, I can still measure the total spin in some region. According to your analysis, I suppose there's no spin sharpening transition.
Spin sharpening. Yeah, I guess the question is, so what do you mean by spin sharpening? Because we need to yeah, SU2 itself, so it's like SU2 breaking to the diagonal subgroup. Yeah, I don't know it. If we have that, basically you have a separate sector of SU2 that you can function product with. Yeah, I don't know. I don't know off the top of my head. It's
I think one interesting thing maybe as follows. So here we first map the system to some stat map setup that has a U1 and the permutation symmetries. But suppose I first map it to something with SU2 symmetry and permutation symmetry. Then the stat map problem may have some tuning parameter such that in one case it has some West-Wiener-Witten term, in other case it doesn't. Then the interesting aspect of the West-Wiener-Witten SU2 nonlinear signal model may be translated into some interesting properties of the circuit dynamics.
Yeah, that's a very interesting comment. So, right, so when I started looking at this problem, the first thing we did is to ask whether it could have a West-Wiener-Witten term, but we didn't think about another copy of SU2. But then, right, so we tried very hard to derive it, but we just didn't find any. But according to the manifold structure, there's a non-single manifold. You expect there to be one, but yeah, we didn't find it. Right. Yeah, maybe with another copy of SU2, this could work out.
Yeah. Any other questions?
Yeah, hi, I have a question. So do we know about the anomaly of this field theory?
Yeah, I guess it's related to the West-Wiener-Witten term, though. It's like
Yeah.
if you look at those classification of circuits, which is one of Chalming's work, like you could classify similar to the temporal ways of topological insulators, and then by looking at a table, you assume okay there could be a topological term, but then but yeah, like I just said, we didn't find one, and it's probably related to the causal structure of those measurement problems, but yeah,
I see.
I don't know.
I see. Thanks.
So in this field theory, there is a fully disordered phase. That's the charge-sharpened area law phase, right?
Yes, right.
Then it means the field theory is anomaly free. There's a fully disordered phase.
Oh yeah, I see. Yeah.
Okay, any other questions? If not, I will thank Haoyu again for the very interesting talk. Thank you. I will stop recording and we can all leave the Zoom.
Recording stopped.
Okay, thanks. Bye.
Yeah, thanks. Goodbye.